Our question for today asks, what is Hund's rule? So, in the past, probably in general chem, if you're like me, you were taught to draw electron configurations like this. If you were given the atom for carbon, which has an atomic number of 6, and you were asked to draw the electron configuration, you would have probably done it like this. You would have said, okay, carbon has 6 electrons because it has 6 protons. So to balance it, we have to give it 6 electrons. So we would start in the first shell with a 1s and put 2 electrons in the first shell in the first orbital. Because remember, the first shell, 1, only has 1 orbital. The s orbital, which can hold 2. So you went 1s2, that's 2 electrons. Then you went 2 second shell, s2. Second shell can have more orbitals, of course, but it always starts with the s orbital. So there's 4 electrons. And then you said, okay, I need to add 2 more to get to my 6, so I go 2p2. Perfect. P orbital with 2 electrons in it. This gives me a total of 1, 2, 3, 4, 5, 6 electrons. So I should be cool, right? Yes and no. In organic chemistry, at least, you need to start understanding something else, which is called Hund's rule, or Hund's rule applies to this other thing you need to understand. And that is that this part right here isn't completely true. Hund's rule states that whenever we have 2 or more orbitals of the same energy level, that electrons tend to fill up different orbitals rather than pair up in the same orbital. So for carbon here, we see that we have 2 electrons in the p orbital of the second shell. How many p orbitals are there for each shell? Well, there's 3. 3 p orbitals for each of the second shell. Okay? I'm going to draw another configuration for carbon that follows Hund's rule and shows you what I mean by this. Okay, so for carbon, we have 6 protons, so it needs 6 electrons, so we're going to start filling it up like this. 1s2, first shell, first orbital has 2 electrons. 2s2. Okay, so obviously we have 2 more in the s orbital of the second shell. Then I'm going to go ahead and draw all possible 3p orbitals for the second shell. I'm not going to put any electrons in them, I'm just going to draw them, okay? So 2p, I'm going to call this orbital x, 2py, and 2pz. This doesn't mean that these orbitals are of different energy levels. All it means, I'm just giving them different names so you can distinguish between each of these 3 orbitals. Okay, so I've already drawn in 4 electrons. I have 2 more electrons to go before I fill up carbon with electrons. Okay, so I need to put them in these p orbitals, right? Because these are full. Hund's rule says that each of these electrons is going to want to go into a different orbital. Both p orbitals, but it's going to want to go in, the first one's going to want to go in px, and the second electron is going to say, I don't want to go in px with this electron, I want to go in my own orbital. So he goes into the 2py orbital. So, just to kind of clarify here, let's really truly draw the true electron configuration for carbon. 1, let me bring it down, I drew that arrow in the way. We have 1s2, 2s2, 2px1, 2py1. That's the true electron configuration for carbon according to the Hund's rule. But let's do one more. Let's do oxygen, because we need to really understand that. Remember that oxygen has 8 electrons. Because it has 8 protons, obviously it needs to be balanced. Okay, let's draw it first like you used to draw it in general chem, or at least how I used to draw it in general chem. 1s2, 2 2s2, that's 4 electrons. 2p2, and another 2p2. That's 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Now let's draw it like we really need to draw it for organic chemistry. 1s2, the first shell is full. Second shell, first orbital, s orbital, is full. Now I'm going to go ahead and I'm going to draw all 3 of my possible p orbitals for the second shell. 2p, I'm going to name this one x. 2p, I'm going to name this one y. 2p, I'm going to name this one z. And notice I haven't put any electrons into this configuration yet. Okay, I have put in 4, so I have 4 more to put in. I'm going to put 1 right here. 1, 2, because this one doesn't want to join this one in the px orbital. It wants its own orbital. It says, I want my own orbital. And so does the next one. It says, I want my own orbital. All right, but now you see we've only put in 7 electrons. We have 1 more to go. He's all by himself out here. He comes over here and he sees that, well, all the orbitals are full, so I'm going to have to just join the px orbital. So, you scribble out this 1 and do a 2. So let's draw it neater. Electron configuration for oxygen, the true electron configuration is 1s2, 2s2, 2p2, 2px2, 2py1, and 2pz1. Maybe you understood this, and maybe you learned this in general chem. I personally didn't. But for organic chemistry, you really need to understand Hund's rule and how it applies to electron configurations so you can move on to things like hybridized orbitals and things.